Kia ora koutou, welcome to the next video on molecules, bonding and structure. This video will be part 2 of the bonding and structure of molecules. This will likely be part 2 of part 3. So the bonding and structure part of molecules is a lot more complex than ionic compounds. So just a reminder, we're doing chemistry 2.4. So previously, the videos we've looked at have been ionic compounds, bonding and structure. And in this video, we're looking at bonding and structure of molecules, and there will be two other substances that we're going to look at the bonding and structure of. So molecules, bonding and structure. In the last video, we started looking at what molecules were. So molecules occur when you have non-metals bonded together, and this bond is called a covalent bond. So we'll look at some examples of this. So let's start with methane. So methane, the formula for methane, you won't need to know the name of it. You would just see it written down as the formula. So methane is CH4. So if we were to see CH4 written down, we would have to decide whether or not methane is a molecule or an ionic compound or a metal. So we need to remember that molecules are made up of non-metals. They're always non-metals bonded together. So we can look at our periodic table that will be given to us in the exam. And we've gone over this in every video so far, but just remember there's that line that you need to remember where to draw in yourself, which divides metals from non-metals. So on this right-hand side over here, we have the non-metals. So we need to look at that formula, which is CH4, and work out which atoms are in that formula. So here we've got a carbon atom, which is on the right-hand side of the line, so that is a non-metal. And remember that hydrogen is a non-metal as well. So carbon and hydrogen, both non-metals. So that CH4, methane, is a molecule held together with covalent bonds. So we'll draw out what methane looks like in terms of those bonds. So remember, this is different to ionic compounds as well, where ionic compounds will donate or gain an electron to form a full outer shell. Whereas with molecules, that covalent bond means that they're actually just sharing electrons, but they still have the same goal, which is to form a full outer shell. So to work out how these electrons are being shared, we need to look at where the valence electrons are in each of these atoms. So we'll start with carbon. We need to look at what the atomic number of carbon is. So we'll look back at the periodic table. And we can see that carbon has an atomic number of 6, which means that when it's an atom, it will have 6 electrons. So carbon's got 6 electrons, 2 electrons will fit into the first shell, and then we're going to have 4 electrons left over. So we would draw 4 electrons, because all we're interested in when we're drawing out these covalent bonds is the valence electrons, so we don't need to draw those first 2 electrons. So carbon has got 4 electrons in its outer shell. Hydrogen has the atomic number of 1. So hydrogen just has 1 electron, and it only needs, because the first shell is its outer shell, it only actually needs 2 electrons to fill up its valence shell. So we would draw all of the hydrogens around each of the lone electrons in carbon like this. And so we can see that this hydrogen has contributed 1 electron there, the carbon has contributed 1 electron there. So this hydrogen feels the effect of these 2 electrons. So this hydrogen effectively has a full outer shell. The carbon atom has shared each of its 4 electrons with 1 hydrogen each. And so overall, carbon has got 8 electrons. So that now has a full outer shell. So each of the atoms in this molecule now have a full outer shell. So now we'll look at a harder example than methane. We'll look at one that the word will be familiar for a lot of us. It's CO2. So carbon dioxide. So if we look at carbon and oxygen on the periodic table, we can see that carbon and oxygen, they're both non-metals. So this must be a molecule. And we want to visualize doing these. This is a Lewis diagram. visualize using the Lewis diagram how this molecule would look like. So remember, for this standard, the molecules that we're going to get will only ever involve one central atom and a maximum of 4 atoms around it. So this molecule here, this methane, is the molecule that will include the most number of atoms that you will see in this topic. You won't ever see any more atoms than this in a molecule. So there's always going to be one central atom for these Lewis diagrams. So to work out which atom is going to be the central atom, we would draw the Lewis diagram of each of the atoms. So carbon, we've just done carbon there, so we'll draw that out. That carbon has got 4 electrons in its valence shell. Oxygen has the atomic number of 8, so 2 electrons will go into the first shell, leaving 6 electrons for its outer shell. So we're going to go 1, 2, 3, 4, 5, 6, and then there's 2 oxygen, so obviously the other oxygen will be the same. So the atom of these two that has the greatest number of lone electrons is the one that you'll put in the middle. So this carbon here has got 1, 2, 3, 4 lone electrons. This oxygen has got 2 lone electrons. So because carbon has got more lone electrons than the oxygen does, we'll put the carbon in the middle and we'll put the oxygens around it. So we'll do that over here. Carbon, carbon, 1, 2, 3, 4, and now I'll put 1 oxygen here. Oxygen, 1, 2, 3, 4, 5, 6, and then another oxygen here. 1, 2, 3, 4, and then what do we? This is a bit tricky, isn't it? 5, 6. So we've got the carbon in the middle with 2 oxygens on the outside, so you're always going to get a central atom. So this is the central atom here. But we need the same rule still applies. So we still need 8 electrons for each of these atoms. So each atom needs to have 8 electrons in its outer shell, needs to fill up its outer shell, even though some of the electrons will be shared. So for the carbon at the moment, it has got 1, 2, 3, 4, 5, 6. So carbon only actually has 6 electrons there. Each oxygen, how many electrons do these have? 1, 2, 3, 4, 5, 6, 7. So the oxygens don't have enough electrons either. So we need to work out a way to give each of these atoms 8 electrons in their outer shell. And so the way that we do that is by using what is called a double bond. So we would, that is where there are 4 electrons shared within the bond. So for carbon, I'll just rub those 2 electrons out there. So carbon will actually be sharing 2 electrons, so it'll contribute 2 electrons to the bond. The oxygen will contribute 2 electrons as well. And then I'll do the same with the other carbon and oxygen. So that carbon's contributing 2 electrons. The oxygen is contributing 2 as well. I'll get rid of the other one there. So now what we're seeing is that with this bond, there are 4 electrons that are being shared between carbon and oxygen there, and 4 electrons that are being shared between carbon and oxygen there. So we'll count up how many electrons each atom has. So this carbon has got 1, 2, 3, 4, 5, 6, 7, 8. So that's perfect. So it needs to fill up its outer shell, which has 8 electrons. So carbon is all good there. Oxygen, 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons for this oxygen as well, and this oxygen is the same. So now we're going to look at 2 more examples, but these are exceptions to what we call the octet rule. So the octet rule is where that second and third outer shell need to be filled up with 8 electrons. So there's 2 examples which don't need their octets filled. And those examples both start with B. We've got beryllium and boron. So we'll do one example for each of those atoms. So we'll start by looking at beryllium dichloride. So we'll put beryllium the middle. We'll look at the lowest structures of each of the atoms first. So beryllium has the atomic number of 4. So we can look back at the periodic table. So it's got the atomic number of 4. So we're going to have 2 electrons in its first shell, and then 2 electrons in its second shell. So 1, 2, just like that. So it's only got 2 electrons. So we, in this example, sorry I haven't drawn it down, we're going to do beryllium BeCl2. So we need to look at the lowest structure of chloride as well, chlorine rather. So chlorine has the atomic number of 17, so it's going to have 17 electrons in its outer shell. We'll just work out how many, 17 electrons in total. We'll just quickly work out how many electrons it'll have in its outer shell. So 17 electrons, 2 go into the first shell, leaving, means that there's 15 electrons left. Then we're going to put a maximum of 8 in that second shell, which leaves us with 7 electrons. So we're going to be able to fit all of those 7 electrons in the third shell. So chlorine has got 7 electrons in its outer shell. So when we draw the Lewis structure of chlorine, all we need to draw are the electrons that are in its outer shell. So we'll go Cl, and remember you just start one at the top, one on the right, one on the bottom, one on the left, and then go all the way around until you've used up all of the valence electrons. So we've got 1, 2, 3, 4, 5, 6, 7, 7 electrons there. So we've used up all of the valence electrons. So this would be the Lewis diagram for chlorine. So beryllium, how are we going to do BeCl2? I'll draw another chlorine here because we've got 2 chlorines in this molecule. 1, 2, 3, 4, 5. Just going to cheat a little bit, go back the other way. 7, 8. Oh, sorry, 7. So we can see we've got 1 lone electron there, 1 lone electron there, a lone electron there, and a lone electron there. So we can share these electrons. So beryllium can share an electron with that chlorine, and that chlorine can share an electron with beryllium. Sorry, they've drawn these atoms quite far apart, but normally we would draw them a bit closer together. And then on the other side, beryllium and chlorine. Beryllium can contribute 1 electron, chlorine can contribute 1. So each chlorine now has 8 electrons. 8 electrons in its outer shell. 1, 2, 3, 4, 5, 6. There's a second one there. 7, 8. And then the same with this chlorine. Whereas beryllium only has 4 electrons in its outer shell. And so this is actually, we need to remember this is fine. This is an exception. Is that beryllium only forms 2 covalent bonds. So that is, it only needs those 4 electrons. So beryllium is fine like that. And just while I'm doing this, sorry, I've forgotten to. So this is these circles that I've drawn around each of the atoms, so just to count up how many electrons to make sure it all looks fine. Once we've done that, so once we've done our working, we can then, this is the more common way that you'll see Lewis diagrams shown, is that for each bond, you will draw a line. So we've got carbon, and then draw a line, and in this case, because you've got 4 electrons or 2 electron pairs in total being shared, we would draw 2 lines, and there we're going to draw 2 lines to the other oxygen as well, and we're going to have an oxygen there and an oxygen there. So that would be the Lewis diagram. Oh, and I'll need to draw on the electrons of each oxygen. That would be the Lewis diagram of carbon dioxide. When we're looking at this beryllium dichloride, we will get Be, and so for each of these shared pairs of electrons, we'll just draw a line, and then Cl, just like that. So draw a line, Cl. So that's how we would, and we need to draw the electrons around. This is easy to forget. Drawing the electrons around the outer atoms. So that is one exception, that beryllium only forms 2 covalent bonds. The next exception that we were going to look at was boron. So what do we have with boron? We'll look at boron trichloride. So it's similar to the last one, similar to beryllium dichloride, except we've got boron with 3 chlorine atoms. So boron has the atomic number of 5, so it has 5 electrons. 2 of those electrons will go into its first shell, and then the remaining 3 will go into its outer shell. So boron will have the Lewis diagram of B, 1, 2, 3. So 3 electrons in its outer shell. Chlorine is the same. We've just looked at that before. So we'll draw each chlorine. We'll draw around next to where the lone electron of boron is. So we'll just go like this. 1, 2, 3, 4, 5, 6, 7, and then chlorine. Oh, 1, 2, 3, 4, 5, 6, 7. So each chlorine now with that lone electron is now paired up with the lone electron of boron. So each chlorine has got 8 electrons. Perfect. And this boron has got 1, 2, 3, 4, 5, 6. And this is actually fine for boron. So the other exception, beryllium is one exception, boron only forms 3 covalent bonds. So this is the other exception. So they're the 2 exceptions that you need to know is boron and beryllium. Everything else needs to fill its outer shell entirely. So we'll draw this as a proper Lewis diagram. So we won't include the dots where bonds are. We will draw boron with a line to 3 Cls, Cl, Cl, and then we'll make sure we draw the electrons around the outside of each of the outer atoms. Cool. So that is how to do the Lewis diagrams of molecules, and we've looked at 2 exceptions that you might come across within this standard. So that feels like a nice place to finish this video. So we've just done part 2 of molecules, bonding and structure. Looks like we'll extend it to part 3 and 4 as well. So do like and subscribe, and for more exciting chemistry videos and to watch the remaining parts of molecules, bonding, structure. Thank you.